All right, so sorry for the delay, guys. I should just not talk to people before class if I was smarter. But it's for a good cause, but in any event. So last time I proved the product rule for you guys, right? But I did not, I kind of sketched why the quotient rule is true, but here is the honest to goodness proof of it. So if we look at the quotient of two functions, right, f of x over g of x, and suppose that f prime of a and g prime of g of a exist, then you can look at their difference quotient, right, which would then be this, q of a plus h minus q of a divided by h, right? And then all of these proofs that are directly from the difference quotient, they involve some kind of sketchy, oh, here, just add 0 kind of step, which is why I like what we did last class a little bit better, because I didn't add 0 in our derivation of the product rule, right? I just multiplied the formulas that the theorem of Carr-Theodori gave us, and we kind of like naturally discovered the product rule in that way. But here I add 0, and when I do that, I'm able to group these two terms together and those two terms together by some sort of sneaky algebra. Notice I've multiplied by g of a plus h over g of a plus h here to make that term. And then I've multiplied by, let's see here, and likewise, excuse me, g of a over, I should say, oh, I think I've got a sign error here. This is actually a minus, right? That should be minus because see, see here, like this and that I've multiplied through. So like these two terms is that term, and this term is that term. But anyway, after you see through the sign errors in my current algebra, you can see that what's the limit of this? Well, it's not, this is not limit 0. This has limit f prime of a. I mean, that's what it means for f to be differentiable. That difference quotient goes to f prime of a. This one here, yeah, it goes to g of a over g of a squared, right? This term here goes to f of a over g of a squared, and this is g prime. And that's the quotient rule. The quotient rule says that f over g prime of a is equal to f prime of a times g of a minus f of a times g prime of a, all divided by g of a squared. Right? So this here is our quotient rule. Right? Any questions about this? All right, so there you go. That's the quotient rule. Now, there, of course, is another rule, which I said I proved today, which is the chain rule. But before I do the proof, I want to go over some more examples. Let's do some more examples before I do the proof, just to remind refresh our memory here. So what are our rules? Let me remind you. Yeah, we have the product rule, d dx of f times g is df dx times g plus f dg dx, right? We know that, well, as I just said, the derivative with respect to x of f over g is equal to, we can write it this way, f prime g minus fg prime over g squared, if you prefer that notation, right? And what was the other thing that I started talking about at the end of last class, but I haven't proved yet? Remember? the chain rule. So if we're differentiating f, let's say g of u, so g is not a function of x, but it's a function of u, let's say, then the way that works is we do dg du times du dx. And so what this notation means, this means differentiate g and evaluate at u. And of course, du dx is, well, it is what it is, right? What other, before I get into the actual examples, what other things do we already know? What things should we have memorized going forward? Power rule, right? We know that d dx of x to the n is nx to the n minus 1. Should always keep that in mind. We know that the derivative of a constant is what? 0, right? Derivative of, derivative sine is cosine. Derivative of cosine is negative sine, okay. What else did we learn last time? We learned that the derivative with respect to x of tangent x is what? We learned it was secant squared x. That was from the quotient rule. What else did we learn? We learned the derivative of hyperbolic cosine was hyperbolic sine. We did that one. We haven't done that one yet, but we could. What else have we done? I mean, there's some specific examples we've come across that would be good to just kind of know. How about this? d dx of the square root of x. That's 1 over 2 times. 1 over 2 times square root of x. This is another one that's kind of good to know. The reciprocal function, right? This is minus 1 over x squared. Now, both of those are really just specific instances of the power rule, right? This is n equals 1/2. This is n equals minus 1. So you can derive these from the power rule, but I'll be honest with you, when I have to differentiate something like reciprocal or square root, I don't actually think through the power rule. Like I happen to know these. After you do them about 20 times, you'll memorize them too. It's just a consequence of, well, familiarity breeds contempt or something. I don't know, but no, you love them. You'll the chain rule. So, well, we have product rule, quotient rule, chain rule. Oh, the theorem of Carathéodory? Oh, okay, sure, I can say that. This is kind of less than the sort of thing that theorem of Carathéodory. Basically, Carathéodory just gives us another criteria for differentiability. It says f prime of a exists if and only if there exists phi continuous at a with f of x equal to f of a plus phi of x times x minus a. So that was the theorem of Carathéodory, or sometimes it's called the Carathéodory criterion. It's a way of capturing differentiability of a function. But I would not put this in the same category as like things above. The things above I would expect any Calculus 1 student to know without flinching. The thing below the line I would only like expect from an honors calculus student to like know this deeply. It's not a... Well, I will show you theory, and I will test a little bit on theory, but I test mostly on the other stuff. Like your test one, right? There was a bonus question that was on like the kind of like deeper theory. That very last part was epsilon delta proof, right? Everything up to that point was either like homework or graphical or, so it's not bad to know it, and I would encourage you to put it on your formula sheet, right? And there's a homework problem where I basically already told you the answer in class, but and this will be useful to us as we derive the chain rule. But so these are what we know, right? This is what we have to work with. So let's look at some examples. So I guess I shouldn't have entitled that example. I shouldn't have titled that example, should I? What should I have called this? I should have called this known results, perhaps, or known formulas. Yeah. Right. So can you guys think of something we haven't done yet? How about the derivative of secant? And I'll use theta this time. Derivative with respect to theta of secant theta. What is secant theta equal to? Yeah, 1 over cosine. Myron, you telling me it's secant tangent?
Oh, no, I'm thinking about something.
Okay. I think Myron might have been telling me the answer, but it might have been. We'll find out soon. So what is this? This is a quotient, so we use the quotient rule. So here, identify, basically we're thinking f equals to 1, g equals to cosine theta for quotient rule, right? All right, so we do derivative with respect to theta of 1 times cosine theta minus 1 times the derivative with respect to theta of cosine theta divided by cosine theta squared, right? How's that work out? Let's see here. So the derivative of 1 is 0, right? That piece is gone. And this is what? Minus sine theta. Cosine theta times cosine theta, right? I mean, I'll write it that way to kind of try to lead you guys. Minus minus gives me plus. And so we got what? We got 1 over cosine theta times sine theta over cosine theta. That is what?
Where did the negative go?
Minus minus is a plus. Mm-hmm. So that's what are we looking at here? We've got secant theta, right? And tangent theta, right? So this is one of the things people are encouraged to memorize in this class. But as most things we come across, there's really only a few things, honestly speaking, that you absolutely need to memorize. I mean, do you have to memorize that? I mean, yes or no? I mean, yes and no. I mean, if you know your derivative of sine, derivative of cosine, if you know the quotient rule, if you have a clear mind about what secant means, then you can derive this, right? Mm-hmm. So there it is. Yeah, it's secant tangent. Now, how about this? What if we're going to do the derivative with respect to, let's say, x of cosecant x? I'm going to do this one a little bit different. This is derivative with respect to x of 1 over sine x. All right? And rather than using the quotient rule, I'm going to show you how we can do this one with the chain rule. Okay? See, this is really the derivative with respect to x of 1 over u, right? If I set what? Let u equal to sine x, right? Now, what's the derivative of 1 over u? See, because the chain rule says that this is equal to d du 1 over u times du dx. So this is the chain rule. What's the derivative of 1 over u? Right. We have to change x to u, but it's minus 1 over u squared, right? And what's du dx? Well, what's the derivative of sine? Right. Yeah, just cosine x. Now, if you do this and you leave that as your answer, I'll be very annoyed, right? Like, we should go back to x at the end of everything. So what is u? U is sine, right? So this is equal to minus cosine x over sine squared x, right? No, I wouldn't tell you. You do whatever you want. I mean, in the wild, you can do either. I might say use the quotient rule to do a specific problem, but I wouldn't always. Usually I just say differentiate. It's up to you to know which rule to use. So, you know, it's easy to differentiate if you have a clear mind about what you're looking at, right? But I know from grading your test that you guys are still thinking about what's an exponential function versus what's a power function, right? Like you have some sort of underlying recognition issues. Like you need to recognize that function is that function, right? Versus another one. Because in your mind, I see some of you have like confused e to the x and x to the n as being the same function, but they're not. They're very different. X to the n is a power function because the variable's in the base, right? See, x to the n, the variable is in the base. E to the x, the variable's in the exponent. So this is an exponential function. You might expect that this would be called a base function, but annoyingly we call it a power function. But these are fundamentally different in the way they differentiate. Even though they're kind of part of the same formula, right? Something to a power is the underlying pattern there, but where the variable is matters, and the way they differentiate is different, right? Like d dx of x to the n is nx to the n minus 1. d dx of e to the x is, well, e to the x. Now, we haven't talked yet about how to differentiate like 2 to the x or 3 to the x. That's a little bit different, okay? We'll get to that soon. But any questions? Can you clean that up? There's a better answer here, right?
Yeah, I thought about that.
What you got? What you got for me?
Wouldn't you just go back to the CSC? I don't know what it's called.
Yes, the CSC.
Yeah, X, and then the other one would be negative cosine over sin.
Mm-hmm.
Isn't it a cotangent?
That is a cotangent, right? So the 1 over sine is the cosecant, and that's cotangent. So the answer is that the derivative with respect to x of cosecant x is minus cosecant x cotangent of x. Now, this is since we've done this example, now for us a known result. You could put the minus, I mean, you could, I just pulled the minus out front, but you could say cosecant of x times minus cotangent of x. It would just be like, you know, we put minuses in the front of expressions typically. So if on the test, let's say test 2, right, I ask you, show, well, there's two different kinds of questions I would ask. I might say, show that the derivative of cosecant is minus cosecant cotangent, right? If that's the instructions, then I actually probably want you to work through what we just did, or either do this or do the quotient rule, right? On the other hand, I might have a problem where I just say differentiate this, and cosecant's part of the formula. Well, if that's the case, you are allowed to refer to this as a known result. If you don't remember it, or you're not comfortable with this, on the other hand, you could take the cosecant and change it to 1 over sine and differentiate that. You got choices, you got options, right? You can go either way. Let me show you what I mean. 3, derivative with respect to, I'm going to do theta, of theta squared cosecant theta. We're going to use what we just did to do this example. So this is a product of functions, so we use the product rule, right? So we have d theta of theta squared cosecant theta plus theta squared d theta of cosecant theta. What's the derivative of theta squared? Derivative of theta squared is 2 theta by the power rule. 2 theta. So we have 2 theta cosecant theta plus theta squared. And what's the derivative of cosecant theta? We just worked it out down there with x, but we got to change the x's to thetas, right? So minus cosecant theta cotangent theta, like so. And there you go. I mean, that's the answer, right? Now, of course, if you wanted to simplify it, I would pull the theta out, I guess. Theta times 2 cosecant theta minus theta. Ooh, wait a minute. What could I have done? I could have factored out a what? I could factor out cosecant also, right? Theta cosecant theta times 2 minus theta cotangent theta. So if I wanted to simplify my answer, I could do that, all right? Now, unless I say otherwise, you don't have to simplify your answer, all right? If I say differentiate and simplify answers, then I would expect this or something like it as an answer. If I just say differentiate, this up here is just fine. Yeah, I mean, so you guys should remember as you're doing homework, you can check your answers with any variety of websites, right? Like, for example, wolframalpha.com. If you just say differentiate whatever it is you're differentiating, you'll be able to find the answer probably. And if you do your homework that way, then your homework is pointless. But it is also good to check your answer. So I mean, it's well, I think Wolfram Alpha is less of a danger than, like, say, photomath, right? Do you guys know about photomath? I should have told you. Dang it. All right, it's too late. Why am I erasing with that eraser when I have a perfectly good eraser shirt? You know? After you get about a full stick of chalk into one of these shirts, that's when it starts to really get good. Well, that was odd. Okay, so so what's the chain rule say again? So let's say if f is differentiable at g of a and g is differentiable at a, then f composed with g prime of a is equal to f prime of g of a times g prime of a. This is the chain rule. There was an example of this that I worked into your mission 4. Remember? You calculated the derivative of the outside function, you calculated the derivative of the inside function, you calculated the derivative of the composite, and we saw that 60 was 2 times 30 in that homework. That was an example of the chain rule in actual function. But here's the proof. The proof is actually not that. And so by actually, I'm gonna kind of chicken out here a little bit, and rather than giving you the super careful proof by the theorem of Carathéodory, I'm going to give you a slightly more heuristic proof using linearization. All right. So since what's what I mean by that? F differentiable near, let's say, y equals to g of a, we have the linearization of f of y at g of a is equal to f of g of a, all right, plus f prime of g of a times y minus, oh, goodness gracious, this is, I'm so sorry. This is, I meant y plus h. So we have f of g of a plus f prime of g of a times h. So that's what the linearization says, that you can write the value of the function at the point plus the derivative at the point times h. This is the linearization of f. Likewise, the linearization of g at, well, I should say this. Likewise, since g differentiable at x equals to a, we have the linearization of g at x plus h, all right? Well, that's g of a plus g prime of a times h. So then if we look at the linearization of f of the linearization of g at x plus h, what that gives us is the linearization of f at g of a plus g prime of a times h. And so at this point, I have I have an unfortunate like notational trouble I've gotten myself into. I need to like, I want to think about, how can I say this? Let's see here. Well, I'll do some color coding. We're going to think of G of A, right, as being the Y. And we're going to think of G prime of AH, all right? That's this right here. So if you'd like, I could change this H to a different letter so we're not confused about the H, right? Like, tell you what, here's a simple fix. We'll make this a capital H. That's easy to change your notes to a capital H, then we can make a substitution, okay? In other words, I'm saying this right here we can think of as the capital H, right? And this is the Y. This formula holds for Y near G of A, so it certainly holds for Y equal to G of A, right? And so what this is then is f of G of A plus f prime of G of A times H. But what is H? H is G prime of A times H. So I said this isn't quite a proof, it's sort of a heuristic proof, but the idea is basically like this. F composed with, okay, so since F composed with G at x plus H is, to a good approximation, the linearization of F of the linearization of G at x plus H, right? Which is, by the way, equal to F of G of A plus f prime of G of A, G prime of A times H, it follows that this is the linearization of the composite of f of G at x plus H, all right? Yeah, don't get lost in the fog. And so if this is the linearization, then whatever the number that multiplies H there, that's the derivative. So that makes this guy right here the derivative of F composed with G. All right. In other words, that's the chain rule, which is that F composed of G prime of A is F prime of G of A times G prime of A. Now, I'm sorry, I was a little bit vague in the proof here at the moment. If I was, we could do the proof by Carathéodory, and there would be really no gap at all. And that proof is in the notes, so I think I've already spent enough time here on it at the moment. But if you look at page 174 of the notes, I have a more sort of, and actually it would have taken me just as long to write that down. So my apologies. But this is essentially the reason that the chain rule holds is when you take a function, right, and we're describing, what is the derivative for a function, right? The derivative for a function is the slope of the tangent line, right? And when you compose two functions and you look at the derivative, if you look at the slope of a composite of two functions, it turns out that the way things fit together, the tangent line for the composite has a slope which is formed by the products of the tangent, the slopes for the tangent lines of the functions being composed, and that's what the chain rule says. And this is really just a consequence of the fact that when you compose two linear functions, the composite of two linear functions, the slope of a composite of two linear functions is the product of the slopes. I don't know if you've ever seen this. Have you guys ever seen this? You've probably never seen this. We should do this in pre-calculus, but I don't think we always do. So this is just a little pre-calculus refresher. Maybe it may help this be less mysterious. If we had f of x equal to 3x minus 2, and you had g of x equal to, 7x plus 5, and you looked at f composed with g of x, how's that work? It's been years? Well, it is time to get back into it. Let's see here. So 7x plus 5, right? Then we do 3 times whatever the input is. So what do you got? You got 3 times 7. You've got 21x. Right. 13. But the key here is that 21 is 3 times 7. It's the product of the slopes of the lines composed. In the same way, that's what the chain rule is saying. It's saying that when you compose a function and another function, the slope of the composite is the product of the slopes of the functions composed. Right. Yeah, but the difference for curved functions is that the slope depends on the point. So we don't see that f prime of g of a in this example, right? Because the slope of linear functions it's 3 everywhere, it's 7 everywhere, right? So you can't really see this aspect of the chain rule in that example, but it really is that. And if you look at what I did here, what I did was I composed two linear functions. I'm arguing that the composite of the linearizations is in fact the linearization of the composite. So, all right. Now that you're back, I'll do something useful. I was just blathering on about like the composite of linear functions being a linear function, and that really being at the heart of the chain rule. That's most of what I said. Fingerprints. I don't know if those are mine. I used to work with somebody, and I swear they'd have like a cheeseburger or something for lunch, and then they'd lecture, but they tend to erase with their hand. So like, it's bad. I mean, the students got him a mitt that he was supposed to erase with, but I mean, well, the thing you have to understand, we didn't have chalkboards, right? They're all whiteboards, so like you erase the whiteboard markers with your hand. After a while, it gets kind of like this. It's just not good. All right, well, let me get back to the examples. Let's do lots of examples. Trying to make sure. Last class, I ended up writing stuff like past here, and then I never panned over. I'm like trying not to do that. Okay, so examples. How about d dx of the cosine of x times e to the x? So what we're going to do here, derivative of cosine, right? So this is, we're going to think of this as being the u, all right? And so we have d dx of cosine of u. Yeah, you're getting ahead of me. That's good. So that's du of cosine of u times du dx. That's the chain rule, right? But what was the derivative of cosine? But we don't write x, we do minus sine of u, right? And then d dx of x e to the x, aha. But that's a what? Yeah, exponential, but it's also a product, right? We have to do the product rule. So we've got minus sine of u. We got dx dx e to the x plus x derivative of e to the x. But the derivative of e to the x is? No, derivative of e to the x is just e to the x again. Oh, you're saying this one. This one's 1. Very good. Yeah, that one's 1. dx dx is 1. Right. So what we got? We've got minus the sine of x e to the x times the quantity e to the x plus x e to the x. You want me to simplify? All right, you talk me into it. All right, so I'll do minus e to the x times 1 plus x times the sine of x e to the x. If I was going to simplify my answer, that's what I would do right there. Again, the step right above it is a perfectly good answer if I didn't ask you to simplify. We good? Okay. Right.
Oh, no, I was talking about the negative sign. I didn't know how you got x, like negative sign, x, x, but then you just plugged it in.
Yeah, that's right. So let me show you another example here. d dx of sine squared x. All right? So what this means is d dx of sine of x squared, right? So the outside function is the square function. What's the derivative of the square function? It's twice 2 times whatever the thing is, right? So the chain rule here says 2 times the sine of x times the derivative with respect to x of sine x. So the answer is 2 sine x cosine x. What can you guys, I mean, it's kind of obvious. What's the difference between my example 1 and my example 2? What did I not do in example 2? I did not make explicit my u. I didn't write u equals 2 sine of x, right? That saved me a bunch of writing. But you got to be careful. If you know what you're doing, you can write it like that. But you got to know what you're doing, right? So I would encourage you to write down the u step until you're properly bored of it, right? And I will sometimes ask you to like explicitly write the u that you're using or something. You know, I mean, I try not to do that too much. Like mostly I just, on the next test, I say, here's some formulas, differentiate them, you know. I don't want to, I try not to bind your hands too much in the process. But okay, so another example. Derivative with respect to x of, how about hyperbolic sine? So first of all, what is hyperbolic sine? Hyperbolic sine is 1/2 e to the x minus e to the minus x was the definition of hyperbolic sine. So I use linearity here, 1/2 d dx of e to the x minus 1/2 d dx of e to the minus x, right? So what we got? We got 1/2 e to the x minus 1/2. Let's say, do you guys want me to put down the u step? Okay, I'll make the u step. So this is 1/2 d dx of e to the u, where u equals to minus x. Chain rule says that that's minus 1/2 d du of e to the u times du dx, right? We always have to multiply by the derivative of the inside function u. That's the chain rule. But of course, that's 1/2 e to the x minus 1/2 e to the u times minus 1, right? Du dx is minus 1 here. Minus minus gives me plus. I'll factor the half out. And we got 1/2 e to the x plus e to the minus x. Undoing the u substitution. And what is that? Well, that is what we call the hyperbolic cosine. This, by definition, is hyperbolic cosine. So there you go. The derivative of hyperbolic sine is hyperbolic cosine. But the derivative of cosine is hyperbolic sine.
Yeah, because I was just going to look at it and say hyperbolic. I was thinking about it in the inverse.
Isn't that kind of funny, right? There's two minuses, though. Minus times minus give me plus. Because of the -1, right? This -1 and that minus give me that plus, and I factor the half out. Du dx. It's a good question. Let's see here. Here's another one. Let's let f of x equal to x squared over the square root of 1 plus sine of x. So differentiate that. What do we got? What are we going to have to use this time? I mean, we don't have to use it. There are two ways to go here. We could either do this as a quotient rule, or we could do it as a product rule. First, I'll show you the quotient rule way, okay? That's kind of like the most sort of obvious thing to try here. So that's derivative with respect to x of x squared, right? Times the denominator function, which is 1 plus root sine root x. The root square root is 1 plus sine x, yeah. And then minus x squared ddx of the square root of 1 plus sine x, yeah? All divided by the denominator function squared. So I'll do the easy part, derivative of x squared, 2x. I picked the low-hanging fruit. There you go, 2x, square root of 1 plus sine x, minus x squared. And so this here, right, is a composite function, right? You can think of this as being like the square root of u, where u is equal to 1 plus sine x, right? So the chain rule on that piece gives me 1 over 2 times the square root of u times ddx of 1 plus sine x. And the square root of something squared is just the thing again, right? So I just get 1 plus sine x downstairs. Do you guys follow? I'm using the chain rule to calculate the derivative of the denominator function this time, because the denominator is a composite function. But of course, the derivative of sine is what? It was cosine. And so what we got is 2x square root of 1 plus sine x minus x squared times 1 over 2 times the square root of 1 plus sine x times cosine x, yeah? All divided by 1 plus sine x. There you go. Now, you could simplify this, right? I mean, you could clear out the square root, multiply. I mean, if I was to simplify this, what I would do is I would multiply the top and the bottom by the square root of 1 plus sine x. And if I did that, what would happen? That would give me a slightly nicer answer. It would give me 2x times 1 plus sine x minus x squared cosine x. There's a half here. All divided by 1 plus sine x to the 3/2 power. So if I was to simplify it, that's what I would do. All right. Now, I said that you could also do this without the quotient rule. Can you guys tell me? How would you do this derivative without using the quotient rule? Power rule? Product rule. I said the product rule? I already gave it away. How would you rewrite that as a product? How would you rewrite this function as a product of functions? How about this? What we're really looking at is ddx of x squared times 1 plus sine x to the minus 1/2 power. That's what that is. It's a product of x squared and 1 plus sine x to the minus 1/2 power. By algebra. And then I can use the product rule. So this is, derivative with respect to x of x squared times 1 plus sine x to the minus 1/2 power plus x squared ddx of 1 plus sine x to the minus 1/2 power. And that is going to give me 2x times 1 plus sine x to the minus 1/2 power plus x squared, power rule, minus 1/2, 1 plus sine x to the minus 3/2 times cosine x. Let me explain what I just did. This is d du of u to the minus 1/2 is minus 1/2 u to the minus 3/2, right? And du dx is cosine x, where u is equal to 1 plus sine x. So most students who are good at calculus, by the time you're to the end of this course, this kind of derivative, you can just write down, going from here to here like that. Like that's your aim, is to get to the point where you can just go from here to here with confidence. But for the moment being, you probably need to write out the u steps, right? Until you're like on the solid ground of knowing what you're doing, right? The minus 1/2? That's because it's the minus 1/2 power function here. This is a u to the minus 1/2 power. And if you look back at the other answer, you see that you could have simplified that as to a sum of two functions, where the first one was just 1 over square root, 2x over square root of 1 plus x sine x, and the second one would just have a 1 plus sine x to the 3/2 power. You can see this piece right here as being that piece. I mean, it's the same answers. This is the thing, is you can differentiate it. As long as you differentiate using correct rules, you're going to get to the same answer, right? So what I'm telling you is there is more than one correct way to do a problem. The answer is not ambiguous, right? It's not like there is a right answer to find, but there's not necessarily a only single right way to do it. Yeah. Okay, so move on to another one. So what do you guys want to see more of? Chain rule, product rule, quotient rule? What's your preference? I think chain rule is what gives people most trouble. Let's work at more chain rule. All right. So let's look at, what is this, 6? I've lost track. Let's look at the derivative with respect to x of the square root of 1 plus the cosine of 2x. All right, so this is d dx of the square root of u, right? Where u is equal to 1 plus